Hello. Today's lecture is about energy and oscillation. Then let's go ahead and then start. Uh, so there are different forms of energy. Mechanical energy, one of the things that we will be focusing on in this chapter. Chemical energy, electromagnetic energy, nuclear energy, etc. Now, what do we need to consider energy? Then remember that energy can be transferred from one form to another form. And the total amount of energy in the universe is always conserved. It means it never changes. It's very essential. Energy is very essential in the study of physics, chemistry, biology, geology, astronomy, and so on and so forth. Okay. So, and then the energy, the law of energies and other things that we will be looking at in this chapter, they can be useful in the law of Newton's laws. Like, for instance, it could be a certain problem that Newton's laws cannot solve, then probably you will be able to apply the energy equation and then you can solve it. Now, to start with, what is work? So before we go ahead and then start like our definitions of energies and the different kinds of energies that we will be talking about, then the first thing that what we need to know is like, what is work? So, in every day-to-day conversation, you may say like, I'm sitting here and I'm lecturing you. Then you may say that like, I'm doing some work. Okay? But in reality, to have a work done, a force must be applied and the object must be displaced, or an object should be like relocated from its original position. Okay? So in general, like, there has to be a certain amount of force, as you can see here in this simple diagram. There's a crate, then you apply a force. You apply a force on the crate. You have this force, and which is a vector quantity, and then you transport it to a certain location. By doing so, the object is displaced by delta x amount. You can just simply say like, you have F amount of force and the amount of distances traveled. So in this scenario, what you need to pay attention is the force and the distance are in the same direction. Then as a result, like, we will have the amount of work done over here is equivalent to the amount of force that you constantly apply throughout the trip. Multiply that by the distance. Okay, so work done is equivalent to force times distance. So, but the other thing is like, then now you need to ask a question like, does it mean like every time I'm applying force, am I doing some work? The answer is going to be no. As you saw it like in the previous slide, there has to be force in the direction of displacement. So therefore, there has to be like there's an amount of force that contributes in the direction of the force. That means like, if you look at here, we already said it. If you drag this crate or box F in this direction to a distance of d, then you are doing some work. If you are pulling your handbag or your traveler's bag F, and then you're pulling it to the airport to a distance of d, you are doing some work, because this force has a certain component that is in this direction. Okay, it has some part of the force that pulls this object is in this direction. Okay, but in some instance, like, you might have a force that you are applying Like for instance, we'll come to the next slide. Let's say that, like, you know, you have a pail of water. Okay. And then you are carrying it. This is how you usually carry it. You're applying force in this direction, and then you will be walking in this direction. Okay. The amount of work done on the pail in this particular case is 0. Okay. That means forces that are perpendicular to the motion do not work. Okay. Okay. So therefore, if the force and the distance are perpendicular to each other, there's no any force that you will be doing. Alright. So there are a few items, like, you know, that you will be interested when you are dealing with, like, work done is equal to force times distance. Within that equation, it doesn't say how much time you took. It doesn't say like how the velocity was varying or changing during the application of the force. Okay. So this equation, like most of all, has its own drawbacks. There's no any kind of like unified equation that can explain everything anyway. Work is a scalar quantity. Okay. Work is a scalar quantity. It doesn't care about the direction. Okay. But keep in mind, it can be positive, it can be negative. Most of the time that we saw, like, velocity can be negative, acceleration can be negative. Those are vector quantities. But unlike most scalar quantities, work can be negative. Because mass is a scalar quantity, and then negative kilogram doesn't make sense. Time is a scalar quantity, and the negative value of time doesn't really make sense. But on the other hand, work can be negative. Then what is the SI unit of work? So if you look at like the equation for work, which is work is equivalent to force times distance, right? We already know the SI unit of force is Newton. And we already know that the SI unit of distance is meter. So therefore the SI unit of work done is equivalent to Newton meter. But this Newton meter has a special name known as joule. Okay, that Newton meter is joule. So in short, you may say the SI unit of work done is joule. Then that joule is equivalent to Newton meter. Or joule can also be the same as kilogram meter square per second square. Because if you remember, 1 Newton equals kilogram meter, right? Meter per second square, right? So therefore, if you substitute this in place of Newton, then you have another meter times meter, it makes it meter square. Okay. So in the US customary, you can measure work done as foot-pound. Okay, but it doesn't have any special name like in the SI unit system. All right. So we already mentioned that, like, the work done by a force that is perpendicular to the distance doesn't work any work. Okay, doesn't work any work. Then what if you have multiple forces acting on the object? And how are you going to find the total amount of work done on the object? So whenever you have multiple forces, what normally do is, like, it's going to be the work done is equivalent to the algebraic sum of all the forces, all the work done by the individual forces. So you find the work done by force 1, find the work done by force 2, find the work done by force 3, and so on and so forth. Then you add them together. Okay. As it's mentioned earlier, Even though work is a scalar quantity, then sometimes it can be positive, sometimes it can be negative. A negative work done, what do you mean negative work done? Negative work done is like a work done by a force that is opposite in direction to the distance. You can experiment the following, for instance, like you have your, in the table, at home, there's a table that like, okay, you push the table with 10 newtons of force to a distance of 10 meters. But throughout this 10 meters, there is a frictional force of equivalent to 2 Newton. Okay. So you may wonder that like the frictional force is like this guy is moving in this direction, the table is moving to the right, whereas the frictional force has been always acting in the opposite direction. You may wonder that like, what am I going to do with that frictional force? Of course, it's going to be a minus. So therefore, the total work done, you just say simply like the work done by F, by the main force, right? There you have. It's going to be 10 times 10, which is 100 joules. The work done by that small frictional force is 2 times 10. But keep in mind, since this is a frictional work done, then it's negative 20. The total work done, or the net work done on the table, is going to be 100 minus 20, which is 80 joules of work. Okay, so just be reminded that work done can be negative, work done can be positive. Okay, this is one of the examples when work is zero. If you look at here, like if you are carrying a pail of water or milk, and then you are carrying it from position X to position B. During this period, your force, or the force applied on the pail, that means by your hand, is acting in the upward direction. But if you are walking like in this horizontal direction, what happens? Those two things are perpendicular to each other. As a result, there is no any kind of work done by the force on the pail. So something that you need to remind is like work doesn't really happen by itself. Even the sentence that we use about work is like work done on something. Always there has to be that on. Work done on your backpack. Imagine the work done you did on the table by moving it from one location to another location, and so on and so forth. Okay. So one more example I'd like to explain here. So you have your backpack here. So this is home. You're at home. Your backpack was like lying on the floor. So you picked it up, put it on your back. Okay. And then you're walking to school. Probably 2 miles, 3 miles. Came to your classroom and you put it on the floor. So, can you identify the locations where you did work and where you did not work? You did not do work. You may consider that's also a handbag. Your handbag, you picked it up from the floor, from your house, and you are holding it in your hand or on your back, and then you were walking for 2 miles. Get to your office or your classroom, and then you put it on the ground. So, how much work did you do? What if I give that information like in terms of numbers or something. The only time that you did work is when you lift the back up and put it on your back, or when you lift it and hold it in your hand. But while you are walking, you are carrying it. That means you are keeping it from falling. That means you are applying force in the upward direction. But you are walking in this direction, so perpendicular to each other. There is no work done in all this instance. The only time you work was when you lifted it up and then put it in your back. And then when you reach here, when the time like take it off your back and put it on the ground. Those are the only times that you did work. For the other 2 miles, no, you did not do any kind of work. Okay. All right. So work doesn't happen by itself. It doesn't happen by itself. It means it has to be done on one object by another object. So there has to be an actor, and then there has to be an object that you would like to act on. It means work then has to be done on an object. Okay, so you know this italic on that you see, okay, it's important, on the object of interest. Okay, now we talked about negative fork. So work done by friction is negative because it's a dissipative force. It's something that holds you back not to do the work. Okay, and most of the time that energy is lost somehow, you know, quote unquote lost, but it's transferred into heat, right? When you rub a certain surface, it just heats up, right? So you are doing some work, but that energy is somehow transferred or converted to something else, to heat energy or to sound, something like that. Okay, so work done by friction is negative. Okay, keep that in mind. So I want you to go and look example 6.1 in your text. Otherwise I'm going to read it for you, and may probably be interested in solving it pretty quick. Problem states like a crate is pulled a distance of 4 meters across the floor under the influence of a 50 Newton force applied by a rope on the crate. What is the work done by the 50 Newton force if the rope is horizontal parallel to the floor? The rope pulls at an angle to the floor so that the horizontal component of 50 Newton is 30. Okay. This is a very interesting example, because it has like the 2 elements that we have been talking about. So first, you're given parameters. The first scenario is like this. There's a crate and it says like you're applying force, and this force is 50 Newton. Okay, and then you moved it to a new location, distance of 4 meters. Then required, what is the amount of work done? So solution is just finding the right equation. Work done is equivalent to force times distance. Okay. Work done is equal to force times distance. And you apply this equation because both the force and the distance are in the same direction. See, the distance is this, and the crate moved in that direction. That's what your D is. So therefore, your work done is going to be your force, which is 50 Newton multiplied by 4 meter. Then that will be 200 Newton meter. But that Newton meter has a special name known as Joule. We already mentioned that. Okay. Simple. Now let's go ahead and then look at part B. Part B says like, now the 50 Newton force is acting like this. The 50 Newton force is acting like this. Okay. And it has two components. Two components means like, instead of, that 50 Newton force acting like that, those two forces can replace it. It's like, how do you represent, how do I say it? Like, for instance, if you have $1 and you replace that paper money into 4 quarters, both are the same thing. Okay, they both have the same effect, they both have the same buying power, they both have pretty much everything similar to each other, except that like one is in another form. So instead of having that 50 Newton force, you may replace that 50 newtons of force by those two forces. Okay. Then the distance is still the same, 50 meters. So what is happening is like, instead of having that 50 Newton, now what if we replace this 50 Newton by two forces. So the 50 Newton by itself acting at an angle is the same as two forces acting on an object like this. So now my question is like, which one of those two forces will do a work? The 40 Newton or the 30 Newton? So according to our definition of work is equivalent to force times distance. Force and distance must be in the same direction. Okay. So therefore, work is equivalent to 30 times 4 Newton meter. So therefore, work done is equivalent to 120 joules. Simple. How about the 40 Newton? No work is done. By the 40 Newton. Since it acts perpendicular to the distance. Okay. All right. Does that make sense? Now, let's go ahead and then like see a new thing that usually comes along with work, known as power. Okay. Power. So what is power? What is power? Power is defined as the rate at which work is done. the work at which work is done, or the rate of energy transfer. In other words, or mathematically speaking, rate means time, how much work is done per time. So therefore, power can easily be calculated as how much work is done per unit time. How much work is done per unit time. So therefore, sometimes if force and average speed are given, then you may find power as force times average speed. Okay. As you know, the SI unit of work is joule, and the SI unit of time is second. So therefore, the SI unit of power is joule per second, and that has a special name known as watt. Okay. Now, if you want to write it with full, so joules over second is watt. Okay. So 1 watt is equivalent to 1 joule per second. Okay. So keep in mind, sometimes it's a very common confusing like to have two W's hanging out together. Like you have a W here, you have a W there. Then how do you know like which one is what? Is this watt or work? Is it like 10 work or 10 watt? A number follows a unit. Followed by a unit. So therefore, this is watt. Watt is unit, whereas work is a physical quantity. So mostly you find work in an equation, in a formula, whereas you will find watt right next to a number. Okay. Now, in the US customary, watt can also be calculated as foot-pound per second, with a special name, horsepower. Horsepower. For instance, like mostly in cars, like when you turn on your TV and then you watch a TV, and then most of the time you see cars being advertised as horsepowers. Oh, this car is such and such horsepower. That car is such and such horsepower. What does it mean? It means like the higher the number, the more powerful the car is. That means it can do more work within a short period of time. Okay. You may see like one car, probably from 0 it may achieve like 60 miles per hour in 5 seconds. Another car may start from 0 to 60, let's say in 10 seconds. This car has a very good kind of miles per hour. This is not meters per second, miles per hour. Okay. This has a very good initial power. Like, most of the time, look, like those fancy cars, expensive cars, like they can reach like certain speed in a very short period of time, because the engine is capable of providing that, and they can drive faster than the regular cost. Okay. All right. So every time when you hear like that horsepower, it is power. They're measuring the power of the car. Okay. Now there is another physical quantity that's mostly you hear it like being associated in round power. Is known as kilowatt hour. Okay. Kilowatt hour. But kilowatt hour is the unit of energy, it's not the unit of power. So for instance, if you look at your electric bill, most of the time the electric bill says 15 cents per kilowatt hour, something like that. Then are they charging you by power? No. They are charging you by energy consumed. That kilowatt hour normally measures energy. Okay. Then having said that, like, then what is the relationship between 1 kilowatt hour? So 1 kilowatt hour, how many joules is it? We know that the SI unit of power is, the SI unit of energy is joule or work. They're pretty much the same thing. Okay. All right, then 1 kilowatt hour, because you know that the SI unit of watt is joule over a second, right? So if you do crisscrossing here, joule is equivalent to watt second. If you convert this to watt second, then you find the joule equivalent of it. Okay. Then kilo means 1000, right? Instead of kilowatt, you have 1000 watt. In 1 hour, you have 3600 seconds. If you multiply this, what's going to happen? You will have 3,600,000 joules. 1 kilowatt hour is 3.6 megajoule. Okay. So now let's jump to concept of energy. Energy is related to work. Energy is defined as the ability to do work. We said what is work? We already defined what is work is. The ability to do that work is known as energy. So there are really main two kinds of energy that we will be dealing with in this material. First one is kinetic energy. Second one is gravitational potential energy. We'll come to that later. So kinetic energy is defined as the type of energy of an object by virtue of its motion. By virtue of its motion. By having speed. Certain object, since it has a speed or motion, then therefore that guy has energy. And the type of energy that it has is kinetic energy. So that means if you have a small ball and then you kick it from one side of the field to the other, then it, as far as like it has speed, or we can represent it as v, you can call it the magnitude of the velocity, and it has mass, then by virtue of having that mass and that velocity, then it has a kinetic energy. Then the kinetic energy of an object can be calculated as half times mt times m times v squared. So note this, write this in your formula cheat sheet, because yeah, it's an easier way to refer and to study. And like work done, energy is also a scalar quantity. It's a scalar quantity. Okay. Work is related to energy. Yes, it is related to energy. How? Let me say how. Let's assume, like, let's take this. Like, for instance, you're driving in a car. Okay, you're driving in a car, and this car was traveling, I don't know, 5-10 meters per second. Then it has an initial velocity of that much, and then you brought it to a complete stop. So you have a final velocity of 0. Then, of course, there was a force, a frictional force that was constantly being applied. Otherwise, the car wouldn't be able to stop anyway, right? So there was a frictional force, yeah, and there is a distance. You can say that, like, you have work done by friction is equivalent to, the amount of frictional force times the distance, right? But during this period, who brought that change in energy? That's friction. If you consider of like the change in kinetic energy, that means kinetic energy final minus kinetic energy initial, right? There was a change in energy. Okay. So that change in energy lost is the same as like the work done, the net work done on the object. So in this particular case, like changing kinetic energy is equivalent to work done. Okay. So the work done by friction in this particular case is the same as like the amount of energy work done by friction. Right? That means, in other words, like the change in kinetic energy is equivalent to the negative of F times D. Why do we use negative, by the way? Because it's friction. It does a negative work. Okay. All right. Then the other type of energy, like in physics, is gravitational potential energy. There's a spring potential energy and so on and so forth. But let's talk about like the gravitational potential energy. Gravitational potential energy is like the energy of an object by virtue of its location from the surface of the earth or from the surface of the ground. Yeah. By having something at a higher elevation, you are giving that object to energy. Okay. All right. We're going to come to conservative forces probably in a minute, but let's try to see the gravitational potential energy concept. Okay. So by having, let's say, you may wonder like how, like sometimes I usually give this as a good example. Sometimes it can be a lot more elaborate. But let's assume like there is a dam. Yeah, you may consider this like a dam. What is the purpose of a dam? Like, I don't know, Hoover Dam or something. Then, to retain water behind it, right? So it's carrying water, stop water. Then, if you let the water to flow through a pipe, usually known as a penstock, right? What happens? So this water, if you follow like a small droplet of water or this mass of water that is going through this, what is happening is it has a potential energy at a certain height because of having this height from the exit, from the tip of the pipe. It has a potential energy. If you let it to pass through this hole, what's going to happen is like this mass of water, because it's going down, it's losing its potential energy, but that potential energy is not completely lost. What happens? It's gaining it as kinetic energy. So that potential energy is transferred to kinetic energy because the water, when it reaches at the exit of the pipe, it's at a maximum speed. It is speeding up with a tremendous amount of speed. That means it gained a lot of kinetic energy, lost its potential, or say its potential energy is now transferred to kinetic energy. And if you let it hit a turbine, right, then the turbine starts to rotate. So what happens? That potential energy is transferred to kinetic energy, and then if you let the water hit turbine means like some kind of an engine that we use to produce energy, hydropower usually. Then this guy is going to rotate. That means you have now a mechanical energy. It's a machine from the machine, and then this will rotate some coil of wire, and then that will be transferred to electrical energy, and then that electric energy comes to your house. See how the process is? Potential, kinetic, some sort of mechanical, and then it goes to electrical potential energy, electrical energy. But it started as a potential energy from mass of water. Okay, so by virtue of having from a certain location, then you can have another good example is like, let's say there's a coconut, right? You want to crush this coconut. What do? Bring a rock, crush it. Okay, what is happening is like by having the rock high up there, you bring it down and then you crush it. In other words, like, whatever stuff was holding this thing up, you're breaking it apart. That means the energy of the rock, which was potential energy, because relatively it has this h distance from where this thing was. then it had that potential energy, and then it crushes it. Okay, it crushes it. A potential energy was transferred to some sort of work done. Okay, so that potential energy was transferred to, because what we were saying is energy is the ability to do work, so something that helps you do a certain amount of work. So in this particular case, the work was crushing the coconut. Okay, likewise, you have a nail, you want to sink it into a wood or a metal, I don't know, what do? You hit it with a hammer, right? To do the work, you need the hammer. You need to read the hammer. You cannot just simply tap it and then you want like this thing to go in or to sink it. You need to pick your hammer up at a higher height, and then you hit it, it starts to go in faster. That means you are doing work. By having that height, the hammer is doing some work. Okay, so then what is the formula for potential energy? Simple. Potential energy of any object is equivalent to mass times gravity times height. It means if you have a book on a bookshelf, it has a potential energy of this. If this book is heavy with a tremendous amount of mass, if you are here, it can break you. It can break a glass, it can do some work, it can do some damage. You can translate that as a work. It means it has a potential energy. So therefore, potential energy of a certain object relative to a certain surface is equivalent to mass times gravity times height. M is the mass of the object, G is the 9.8 or the 10 meter per second square, and then H is, of course, the height. Like kinetic energy, gravitational potential energy is also a scalar quantity. The SI unit of energy in general is joule. So therefore, the SI unit of gravitational potential energy is also joule. Alright, so we'll continue with this discussion pretty much, it's potential energy as we said it. So, for instance, this book has a potential energy relative to the desk. Probably this is 1 or 2 meter. So in this case, its energy is, probably from the floor can be like 4 meter. From the street level, right? This can have, let's say, I don't know, 20 meter. I'm just exaggerating it, but it's fine. So in all those 3 scenarios, like this guy has different potential energies. Over here, if it falls here, might not really make that much damage. Relatively damage, relatively higher damage. Probably the highest damage can be obtained if you let the book to fall that height and hit something. Alright, okay, so we'll do some examples later about potential and kinetic energies. Okay, see you later.